In this video, we are going to discuss perfect, abundant, and deficient numbers. We need to start with the definition for proper divisor. A proper divisor of a number n is a divisor of n that is less than n. All right, let's talk about examples so we understand what that is. So the proper divisors of 8 are 1, 2, and 4. See how we stopped at 4? We don't list 8, so we never list the number itself. Let's go to another number like 20. So if I list the proper divisors of 20, I want to list all divisors less than 20. So I have 1, I have 2, I have 4, 5, and 10. If I go over to another number like 7, the only proper divisor I have is 1. So every number has a divisor. Every number has 1. If it doesn't have more than that, that's okay, because we don't include the number itself, but we can guarantee that everything is going to be divisible by 1. We also want to note that all prime numbers only have 1 as a proper divisor. Okay, so now that we know proper divisors, we can start talking about deficient numbers. A number n is deficient if the sum of its proper divisors is less than n. So let's talk about 10. Right? We said the proper divisors of 10 are 1, 2, and 5. So if I add 1 plus 2 plus 5, I get 8. 8 is less than 10, so 10 is deficient. Let's pick another number. Let's say we said 23. Well, we know 23 is prime, so the only proper divisor it's going to have is 1. 1 is definitely smaller than 23, so once again, we have a deficient number. Let's talk about a different kind of number. This number is called abundant. So a number n is abundant if the sum of its proper divisors is greater than n. All right, so let's pick another example. Let's say I say 12. 12 has a bunch of divisors. It has 1, it has 2, it has 3, it has 4, it has 6. So now we want to add those up. So I add 1 plus 2 plus 3 plus 4 plus 6, and I get 16. All right, so 16 is bigger than 12. With deficient, we are looking for less than. With abundant, we're looking for greater than. So 16 is greater than 12. That makes it abundant. Let's pick another number. 20. We talked about 20 earlier. 20 has factors of 1, 2, 4, 5, and 10. Again, let's add those up. 1, 2, 4, 5, and 10 gives me a sum of 22. 22 is bigger than 20, so once again, we call this abundant. So let's think about what we talked about. We talked about what happens when the sum is less than the number. We talked about what happens when the sum is greater than the number, which only leaves what happens if the sum is equal to the number. So here we come to perfect. So a number n is perfect if the sum of its proper divisors is equal to n. Okay, so let's again look at an example. So let's pick 6. The proper divisors of 6 are 1, 2, and 3. If I add 1 plus 2 plus 3, I get 6. That makes 6 perfect, right? The sum of the proper divisors, we're right back at the number. Interestingly enough, 6 is the only single-digit perfect number. So that means we don't need to look at any more single digits. Let's go to double digits. So double digits, how about we pick 28? So 28, I have 1. I always have 1. I have 2, I have 4, I have 7, I have 14. So it's really important when you're doing this that you're really careful to make sure you list all the proper divisors. Don't skip any or it'll make it the wrong kind of number. Now when I add them up, 1, 2, 4, 7, and 14, I get 28. So 28 is perfect. Again, interesting, 28 is the only double-digit perfect number. So I usually tell everybody, so far as numbers go this way, we all get to be perfect twice, right? We've all been 6 already, so we've already messed up one of them, right? We've already been 6 and we missed it. We didn't even know we were perfect. The second time is 28, so I just say appreciate your perfect times. So when you turn 28, you can say this year I'm going to be perfect. It's going to be a great year, just from number sense, right? From number theory. So now let's look at some different numbers. I just threw a bunch up there, 22, 48, 41, 100, and 32. And I think you should try these. So go ahead and stop me for a minute and write down all the proper divisors of these numbers, add them up, and see if you can decide if they're deficient, abundant, or perfect. When you're done doing these, come back and check how you did. All right, so let's start with 22. 22 is a small enough number. We know the divisors. We have 1. We have 2, we have 11. Doesn't take a calculator to tell you if I add 1, 2, and 11, it's going to be smaller than 22, so I know it's deficient. And I think that's an important thing to talk about as you're doing these. If you can add it up in your head and kind of see, oh, I know what it is, then definitely do that. Do it for the ones that are really small or the ones that are super big and you can tell. So 48. 48 has 1, it has 2, it has 3, it has 4, it has 6, it has 8, it has 12, it has 16, and it has 24. That is a lot of things to add up. Here's what I think. If I go to 24 and I add 16, I'm already at 40. I add 12, I'm at 52. I'm done. I'm not adding the rest of the numbers. I don't need them. I can quickly tell you this is abundant without ever touching my calculator. Feel free to use your calculator, but when you don't have to, don't worry about it. 41. Well, 41 is prime, so it means it's only going to have one divisor, which is going to be 1. That makes it deficient. And then let's look at 100. 100 has 1, it has 2, it has 4, it has 5, it has 20, it has 25, it has 50. Again, I can see 50, 25, and 20. Well, this is 50, that's 75, this is 95, there's 100, and this keeps going. I'm finished with that. I know it's abundant. I can tell you it's already bigger than the number. 32. 32 is a tricky one. 32 has factors of 1, 2, 4, 8, and 16. It's deficient, but man, was it close. When you add those up, 16, 8, 4, 2, and 1, you get 31. So it's really close to being perfect, but it's not. So I do say when you're not sure about your adding and when you think you need to check it, definitely check it because there's some close calls there that you want to make sure you get the points for. Let's look at where this came from. Most of the time students tell me this is brand new to them. They never heard of perfect, abundant, deficient. Where is this math coming from? And I want to tell you it is coming from 300 BC. So this is Proposition 36 of Book 9 of the Elements, published by Euclid around 300 BC. And what I would say about this book, The Elements, it was one of the highest published books of all times and still is. I mean, number 1 is going to be the Bible, is most published book of all times, but The Elements is ranking up in there too because it's so old and it's just so useful to mathematicians. So what I would call Euclid, and hopefully this makes sense to you guys, it's kind of like Webster's Dictionary where all the definitions are put together. So just because it's in Euclid's Book of the Elements doesn't mean Euclid came up with it. He came up with some of it, but not all of it. So maybe like Wikipedia, right? Maybe that makes more sense in our day. It's a collection of things, right, that are kept all together and published, but all these things were about like geometry and numbers and stuff. So this earliest writing about perfect numbers, I'm going to read it to you and then we're going to break it down. So it says, if as many numbers as we please, beginning from a unit, be set out continuously in double proportion until the sum of all becomes a prime, and if the sum multiplied into the last makes some number, the product will be perfect. Right? So Euclid thinks he's giving us an algorithm. He's given us a process of how to find perfect numbers, but it's not so clear. So let's make it clear. So I've highlighted the important numbers, right, or the important words here. So it says first, if as many numbers as we please, beginning from a unit. So what is a unit? A unit is 1. So he's saying, hey, start at 1. And he says, set out continuously in double proportion. Well, double means just times 2. So it means if I start at 1, I'm going to double it. Now I got to 2. Okay. And then it says until the sum becomes prime. Well, let's see where we started at. We started at 1. We doubled it. We got 2. 1 plus 2 is 3. We're looking pretty good, right? So we started with a unit. We doubled it. We got a sum. The sum was prime. Awesome. Now it says if the sum, so that's 3, multiplied into the last, which was 2, this is our perfect number, right? So he says until the sum of all becomes prime, did it. If the sum multiplied into the last, 3 times 2, did it. Now we have a perfect number. And 3 times 2, if you remember, I said 6 was the only single-digit perfect number. So here was just the rest of it. So my 1 plus 2 is 3. The 3 times 2 is 6. 6 is perfect. Good job, Euclid. Let's try it again, right? Because that's a little, let's go more. So let's go back to 1. We doubled it to got 2. Now we double it again, we get 4. Let's add that up. 1 plus 2 plus 4 is 7. Okay. Then I take the 7. I multiply it into the number before it, which is 4. 4 times 7 is 28. And if you remember, 28 is a perfect number. We said there was one digit number that was perfect. It was 6. There's one two-digit number that's perfect. That's 28. And look at, we found it. So Euclid's proposition is super helpful for trying to find perfect numbers. All right. So let's go more. We were at 1. We doubled to 2. We doubled to 4. We doubled to 8. All right. Check this out, though. 1 plus 2 plus 4 plus 8 is 15. 15 is not prime, which means we're not done. So go back, right? It says you can't stop at 8 because I didn't get a prime number. Double it again, I get 16. Now I feel better. 1, 2, 4, 8, and 16 is 31. 31 is prime, so it says we're in business. All right, so once I get this 31, I look at the number right before it, 16, and I want to multiply. So I do 31 times 16, I got 496. We haven't talked about 496 before, so it's really worth stopping to look at it. And I'm listing here all of the proper divisors of 496. So I have 1, I have 2, I have 4, I have 8, I have 16, 31, 62, 124, and 248. When you add them up, we do get a perfect number. We get 496. So this just shows us, this is us just using Euclid's proposition, and it shows that this is a way to generate perfect numbers. All right. Just for fun, let's talk about things that are important back in the day to this. So St. Augustine, which was 354 to 413, wrote about perfect numbers in the City of God. He said that 6 is a number perfect in itself, and not because God created all things in 6 days. Rather, the converse is true. God created all things in 6 days because the number is perfect. He similarly asserted that the moon traveled around the earth in 28 days because 28 is a perfect number. What I really want to point out here, this is numerology, right? So there's nothing that says any of this is true, false, whatever. But it is saying, what were the two big houses in the world? There were academics and there were the church, and there were a lot of ties relating the two. And I think it's interesting sometimes to look at the history of mathematics and the history of the world and see how they influence each other. And this shows you this was influencing way back that people thought about this numbers and what people were proving and justified it on their own, thinking of their, religious rationale. That was just I think history is always good to look at. How does history influence how we grow as humans, right? And how our brains develop. So that aside, let's look at some of the list of smallest perfect numbers that have been discovered so far. Now, when you look at this list, you might be confused at first. 6 we're good, 28 we're good, 496 we're good. Bounce to 8,128. This is 33,550,336. I have to stop myself so I can read this. This is 8,589,869,056, and this is 137,438,691,328. You could keep going. There are a list of these perfect numbers that are monster kind of huge. What's interesting is so far all perfect numbers that have been found are even. They are also always ending in 6 and 8 that we found so far. So mathematicians believe there are not odd perfect numbers, but we can't prove it, just like we couldn't prove the Goldbach conjecture. And so far, as they've been discovering, they haven't found any that don't end in 6 and 8, which is just kind of interesting too.